about Udacity and what we do here. Udacity is a company committed to democratizing education. And we're not just talking general education, we mean specifically industry-focused education that's meant to get you a job one day. So, for instance, we have a huge library of resources where we teach things like Android taught by the people who created Android at Google, or a course on how to use TensorFlow taught by the head of Google Brain at Google. So we really encourage you all to try out all our courses for free. In addition, we have a set of programs called Vanity Degrees, where we take you from where you are to job ready in a given field you're interested in. We provide you support, career services, and all the support you might need to really empower your own education and your own industry transformation. Specifically, we are going to be doing something in self-driving cars. We're designing a program right now with Sebastian and other industry partners around making you a self-driving car engineer. And we hope to launch this soon, so we quickly wanted to show a trailer about that. That's happening. The first one was at Nvidia about a month ago. And this is a really special one for me because sometimes things in life connect different points in space and time together. And Sebastian Thrun was somebody I knew in the founded roaming the hallways of Wien Hall. We had a little mobile robot lab, little social gatherings when I was at Carnegie Mellon. And I followed the work. I followed the grand vehicle base going across the desert where he competed head-to-head with Red Whitaker's teams. He had a very heavy-handed hardware approach that was applied to problems. And there was a variety of different philosophies kind of in movement during these time periods. And so what I guess I wanted to mention is essentially you get these points in time that reconnect. So Sebastian went on to found Udacity with Peter. He and Peter
subject matter was to build a self-driving car together. Same way we're going to do this here at Udacity Racing. 20 ran away as fast as they could. And 26, we decided we're going to drive the Open Challenge course in exactly 2 months' time. And we're able to drive further than any other Open Challenge team had done from the very beginning of building our physical car to that experience. Now, there were moments that are unmemorable. This is one where we got a decision David Stevens of Udacity, where the car got stuck in mud. We had this misfortunate day, the day the New York Times news is right about us. We had this software glitch, and the car went into a tree, and then eventually got stuck in mud again. And we had asked actually Michael Markov, the New York Times, to help us push it out. And made for a very interesting article. But these are the elements. Our friends from Carnegie Mellon practice was quite a few actually. This is just a few weeks before the race. They decided to, it was too dangerous to the car, so they chased people behind it. No one in the car, because we had people in the car with help.
Here it's a great university. The good old days. Come the race itself, fast forward in October 2005, it's almost 10 years ago, a little more than 10 years ago. We all in the Mojave Desert, 196 teams had lined up to compete. There was a team run by girls from, I think, Palo Verdes High School in Southern California. They had qualified for it and beaten MIT in the race for qualification. It's kind of amazing. 17-year-old girls. It was really amazing. We had all kinds of we had car companies. Ford was there. They didn't disclose who they were. They were afraid of it, that they would embarrass themselves, as they did. The big name at the time was Carnegie Mellon. They actually had 2 vehicles, about 100 people. Chris Urmson, who just left Google, was the technical team leader under Red Whitaker, a great guy. And we had our little love bug, Stanley, which is now in the Air and Space Museum in Washington, D.C., if you ever stop by there. And we were distinguished in 2 ways. For one, we had focused almost entirely on software. We used massive machine learning at the time, whereas almost everybody else had focused on hardware. I always felt making a car drive itself doesn't require stronger tires or different suspension. It really requires a brain. So let's make the brain really big and not really small. And the second distinction is we had a Red Bull sticker on the car, which turned out not to amuse the government, which of course kind of phrased this event as a military event. I mean, after all, it was military funding.
What sticker?
A Red Bull. Red Bull. Red Bull is this drink that keeps us alive. I drank so much warm Red Bull in my life, you wouldn't believe it. I almost lost my teeth over it. But every time the weather was going, a big box came in, and we would all break for breakfast and lunch and dinner. We had no refrigeration, so it was always warm. This is mostly video taken from an hour-long special called The Great Robot Race by Nova, shown here without permission. We were somewhere in a tent basically watching this on a big screen. What we see here is stuff we couldn't see, but they had a helicopter and could pursue it.
Just 5 robots
And
remain on the course.
in the beginning, Carnegie Mellon was leading, then they developed an engine problem, and then we were able to pass them, as you just saw. And the most difficult part of the race was at the very end. It was this treacherous mountain pass. Here's Stanley, covered in mud and dust. Behind Stanley, by the way, is a human-driven car that can stop it in case of an emergency, called Chase Vehicle. And then after just about 6 hours, 53 minutes, we saw in the grandstands where we are collected, first helicopter, a dust cloud, a little blue dot, which was great because Carnegie Mellon's cars were all red. And then eventually, what we built, the car would make it after 131 miles of a grueling desert race, completely autonomously, an unrehearsed desert terrain, back home to win the DARPA Grand Challenge. That was an amazing moment for me and for my team. And I would say for many of the other teams there, it wasn't as much about us winning. I think it was in total 5 cars came back. It was really about, wow, within a year or year and a half, we were able to build 5 cars that can do something amazing, completely impossible before. Just look at the velocity. That was amazing to see that it turned us into believers that this technology could actually work. Again, this is now the car in the Air and Space Museum. It's kind of funny to have a car in the Air and Space Museum. I don't know why. But if you go to the 2nd floor, tucked away behind the lunar lander, you find Stanley for a few more years. I think 2 or 3 more years, and it's going to go in the collection. Fast forward, we had a second race called Urban Challenge, which Carnegie Mellon won, and we came in second. And it was more of a city race, which I don't have any materials in here. But it was an empty city. It was a former military base, and cars had to learn how to interact at intersections and yield and stuff like this and route themselves on the shortest path. Then, by 2010, I decided, Google, which was known to be a search engine company, decided to branch out and do something crazy. So Larry Page, who is kind of the brain behind all this, came to me and said, hey, why don't we build a car that can drive anywhere in the world, or anywhere in California? And I said, that's really hard. He said, that's good. Let's just do it. And we had a whole bunch of conversations, but what we decided to do is we carved out kind of 1,000 reference miles and said, okay, if the car can drive those, then Sebastian, you're going to get a paycheck, extra bonus. So that's awesome, that's great. So I collected myself a small team, and the head of the team was Chris Urmson, the guy who ran the Carnegie Mellon team. I also hired Anthony Lewandowski, the motorcycle guy, and a few other folks. And within 18 months, we were able to drive roads like Lombard Street, Highway 1 from San Francisco to Los Angeles, around Lake Tahoe, all the Bay Bridges, downtown San Francisco, downtown Monterey, completely hands-off. Not always, but we were able to show it once. In fact, one of the things that we're doing under Oliver with Sense over there, who is our head of engineering and product, and we're actually buying a car right now. And the goal is to replicate this, but not us writing the software, but you guys writing the software. We're going to issue some competitions and some challenges and hope to put together a self-driving car that's crowdsourced. And it took about 18 months for Google to do it. I hope we can do this in 3 months. So let's go really fast, because I think it's really awesome to crowdsource the software for a self-driving car. And our nanodegree that's coming up is the core of this. Fast forward, we moved to more comfortable cars with better air conditioning. And then under Chris, after I disengaged as the leader of the team, Chris built these little love bugs that you see zipping around outdoors. These are 2-seaters, low-speed vehicles, go 25 miles an hour. But we really wanted to nail the issue of how to drive reliably with superhuman reliability. On highways, the mean rate between what we call critical interventions, which is when a human driver has to kind of grab the steering wheel to make sure things don't go wrong, is about 500,000 or so miles right now. It's better than human driving. And in city driving, the number is actually very similar. That is, the cars that drive through Mountain View here are completely autonomous, and they're almost never making a mistake. Almost, it turns out, there's been one mistake. A Google car did scratch a bus, but there's been the same time about 20 accidents caused by human drivers that scratched Google cars. So we're in the great scheme of the World Cup of who drives safer. The Google car wins by 20-1, roughly at this point, against humans. Here's my team, my initial team. You can see Chris on the right, Anthony, the motorcycle guy, in the center. And Anthony actually just, as I mentioned, sold Otto to Uber and me. In the beginning of this team, we were in stealth mode, and we were secretly driving these cars around. And for a year and a half. No one had a clue. We had 8 of those cars. And they would do stuff that's pretty challenging, all without anybody noticing the self-driving car. Now, people didn't notice because there was always a person behind the wheel as a safety precaution. But other than that, we were sitting there doing nothing, eating sandwiches. And facing quite challenging, this is fast forward, I should say, but facing quite challenging situations, from toll booths to pedestrians in downtown Monterey. Again, this is fast forward a little bit, to narrow mountain roads. This is Page Mill Road, where trucks push us almost off the road while we are autonomous, all the way to night situations where deer cross the street and so on. This is my favorite thing, Lombard Street. We had a lot of volunteer pedestrians here that assisted us our research unknowingly. So that's kind of what we did before we went public. And then unfortunately, New York Times found out about us and wrote this article. That was actually a nice article. The reporter, John Markov, talked about goosebumps. This was that was my challenge, and the street we're going to carve out for ourselves. We set ourselves a little challenge in Udacity. We started Udacity here, and we drive on El Camino Real all the way to San Francisco. That street was part of the 1,000-mile challenge. This is another one. And you can see, if you know the area, there's a really complicated mountain pass here. You're actually going up Page Mill Road, East Alpine, then you go Stage Road, Highway 1, which is really fast. You go all the way to the marina and then down Lombard Street, back to Market Street. That's not your easy afternoon drive, right? We built these cars, we put lasers on them. They would be in traffic every day and basically drive like human drivers. This is about 2011 right now, it's 5 years ago. You see how the car yields to pedestrians and then moves on. And then you can see, people ask us what the thing is on the top. We kind of have all kinds of reasons. Like, are we looking for extraterrestrial life? It's a windmill that regenerates some of the energy we use for driving. It's amazing how bad people's physics education really is. They believe this. Let me show you some of the stuff under the hood, and this is actually fairly accurate even today. The core workhorse in perception, I'd say 90% of the work is perception, 10% is control in general. The workhorse is called a laser, and this is a scanning laser built by Velodyne, which is the leading company in a research space right now. And you see it taking these scan lines as it scans of objects, and it uses laser light to not just look at the reflectivity and brightness, but also at the range of objects. So it builds literally a 3D model of the environment. 3D is nice because it really helps understand how we can drive around stuff and where people go next. It's in many ways much easier than images. Or that video we talk about, amazing work just using images. It's going to be very, very hot, this field right now. One of the things we did from the beginning is building maps and localizing with these maps. This is an older laser system, still from my Stanford days, but you can see this laser not just mapping the 3D structure, but also what we call infrared remissions, which is the kind of the color of the ground in the infrared spectrum. And those maps allow us to, here's another map. This is a 3D map of Page Mill Road. These maps, many, many different types of maps, allow us to do many things, and one is to localize the robot. So we look at the map and we look at the momentary sensor data, and by matching these things together, we can get about 5 to 10 centimeter accuracy as to where we are. And that makes a huge difference. So in the next video, I'm going to show you, this comes up, it's Lombard Street, I guess, in 3D. This is a little animation of a robot driving on a street using just raw GPS, which is the gray box, or using GPS plus our map. And the error that GPS has is so substantial that you would hit other cars if you drove just using GPS. But by adding this map-based component, we're able to reduce the error significantly. And that's at the core of what's happening. In fact, quite interestingly, if you drive a Tesla, Tesla does not do this. And there's many behavioral implications that you can see where the Tesla acts differently because of the lack of maps. Maps are great because they anticipate things. You can slow down for turns. You know exactly where the intersections are. You can find danger zones, hotspots, like places where people tend to cross intersections and have the right of way. All these things can be baked in advance. Humans can't do this so well because we can't really upload all the streets into our brain, but robots are perfectly fine with us. This is what's called localization. You see a car driving in a map and trying to find out where it is, what I just described. The little red dots are called particle filters, and for those of you who do take my courses, you probably know what they are. For those of you who don't, it's too bad for you, really interesting. Of course, things change, and the most important thing that changes are the participant in traffic. People, pedestrians, bicyclists, other cars. Segmenting them out and understanding what they are is important. Classifying what they are is really important. These are all projects coming up in our nanodegree. And then eventually making a behavioral prediction. What they're going to do next is really important, because you have to know what they do next so you can plan the way you would interact with them. Here's a typical video of tracking on a highway. This one is remarkable because this was really hard for us for a long time. There's a motorcycle coming in the bottom. It's splitting lanes. This is actually illegal in California. It's not a great way to live long, but people do it, mostly young guys. And you can see how our system is able to understand how vehicles have different sizes and different behaviors, including something that seems to not really fit in this task. So this is called tracking and segmentation and prediction. And we're going to talk in another way about technology like this. This is a scene from Vegas Strip. Quite busy. Lots of pedestrians, lots of cars, lots of other stuff. It's about as complex as it gets, right? Just imagine you look at this, you have to make driving decisions. So that's kind of the level of complexity the robot is able to do. Now, right now it's stopped, so there's no driving decision at all. It's like the little dot, but as soon as it starts driving again, it has to interact with all these things, right? And really understand, is it safe to drive? And just the green light doesn't mean it's safe to drive. There could still be a pedestrian running across the street and so on. And this also, you can see some classification errors. What next? Here's putting stuff together a little bit more. A system that can detect traffic lights, senses lasers, classifies the objects around it, understands what they are. In this specific instance, the car tries to turn left, and then there's pedestrians approaching it. And those pedestrians put a blockage that the robot can go because they have the right of way. And you can see how the brain of this robot becomes more and more complex as it reasons about all these point clouds and so on. So here it is trying to give right of way. In fact, here it's actually breaking the law. It's actually blocking oncoming traffic. Shouldn't have done this. We fix this later. But that's kind of what we did every day for many, many years. Just drive around, observe, and then let the robot learn. This is actually an interesting one. This is one where we had an accident that caused by people. So we are in the middle, and someone just bumps into us. Actually, no, it's wrong. Different video. It's a lane change video. Okay, it's autonomous lane change. I think I have one coming up where we do have an accident. This is actually stop sign. This is actually really interesting. In the beginning, I should stop this for a second. Hold on. In the beginning, we always thought stop signs are really easy, right? So you go to the stop sign, and you wait until it's your turn, and you add another 3 seconds just to be safe, and then you go. You can try this out. This is disastrous. If we do this, you never get a chance to drive because everybody's going to cut you off, and the person behind is going to honk their horn. So this is one of the early ones. Is it playing? It's not playing. Come on, play, please. Okay. So you see us come to the stop line. We have these kind of gates for pedestrians. And obviously it's not our turn, so other cars go first. And while we wait, the second one, this is now running, going ahead of us. And we're still waiting a little bit until the turn, but then this guy also kind of cheats us and forces us to stop. So that's San Francisco, this is how stop signs work. So one thing interesting that I learned is even with stop signs and lane changes and so on, there's enormous amounts of communication going on, right? So the way you navigate a stop sign successfully is when you think it's your turn, you inch into the intersection in a specific way. And the speed at which you do it shows how determined you are. And it can deter other people from taking their choice. If you go really fast, you can try this out. And if you go really slow, then people will take advantage of you. And there's this entire communication pattern going on. It's nowhere documented, but you have to understand to drive. We measured all kinds of features about our trained human drivers versus self-driving cars. This is a kind of a histogram of how much braking, how much extreme braking and how much extreme acceleration humans do, and these are trained professional drivers versus cars, and our cars brake much less and accelerate much less. It's kind of interesting. They actually drive nicer. And if you look at the time to collision of how safe is the car in terms of giving space ahead of it, this statistic says in essence that cars leave more space and drive more defensively on highways. So they actually not make themselves safer, they also make the surrounding traffic safer. We program them to make sure that they stay out of the way of other cars if other cars need space in emergencies. These are kind of, this is the video I was referring to. That's the one where we got bumped by somebody. So we're in the center, where the center of the rings are. And typical thing happens, someone's not paying attention, trying to change lanes, hits us, and then a little scratch on the car. I don't know the exact numbers, about 20 of those have happened so far. Sometimes cars got totaled, our cars got totaled, but except for one, it was always humans' fault. And then you see all kinds of stuff that you can't even train. Like here's the one that we observed, and I have no clue what happened. But that's kind of shows you the complexity of stuff happening. When you program them, the first 99% are easy. From the remaining 1%, the first 99% are easy. But then it comes to these freaky moments from deer crossing highways to people doing this, when it becomes really challenging. And if you don't solve those, you might have one bad accident every month, right? And that's certainly not good enough. We started also working with clients. This is still when I was running the team. Have people seen this video? So this is Steve Mahan. He's blind, legally blind. He used to be full seeing until he was about 40 years old, lost his vision. And as a result, his way to work moved from half an hour to 2.5 hours. If you're legally blind, transportation options are very, very poor and really not well developed. So we made him drive a car to and from work quite a bit, and he loved it. So we can go to get food and so on, he'd eat sandwiches while eating. And what we really believe is, this technology has so many different implications, but one it does have is can let people drive who can't drive today. Aging people, blind people, drunk people, kids. It's a dimension where we can have an impact on people's life that just wouldn't exist otherwise. So he is pulling somewhere in and there's other visions. This is a project I did at Google with golf carts. This was unmanned cars on public streets long before the California law passed. This would actually be illegal today. So we built a system where you could basically flag a car using a phone. And we deployed it on campus as campus transportation. And you could, they would come to you, 25 miles per hour is plenty on campus, Google. You could then either drive them yourself if you're so inclined, or you could get some work done and sit in the passenger seat. Either one was fine. But the transformational thing here is, this alleviates car ownership, right? So this is transportation as a service, which means no more garages. There would be no more parked cars in San Francisco, right? This is something that automotive companies are freaking out about, because it also means we need fewer cars. We have about 100 million cars in this country, and 97% on average are parked somewhere, and only 3% on average are moving. So we don't need that many cars. Okay, this is my favorite video. This was done.
Hands-free driving. Cars that park themselves. An unmanned car driven by a search engine company. We've seen that movie. It ends with robots harvesting our bodies for energy. This is the all-new 2011 Dodge Charger. Leader of the human resistance.
They actually showed this in public. Anyhow,
That's my little story about self-driving cars. Obviously, it's become very hot right now, right? So with Uber and Zoox, was my former PhD student, and so many people going in this, including we becoming a self-driving car company here at Udacity. And you guys can all help us code them. But it's a fascinating technology, and I think we're now at the verge where it's becoming real. I want to give you one last thought before I pass on Danny. One of the big insights in building self-driving cars has to do with AI. AI is, as you know, very, very hot right now. And here's how it goes. When we humans make a mistake driving, then we probably learn from it and hopefully never make that same mistake again. But by and large, nobody else learns from it. So we all keep making the same stupid mistakes over and over and over again. That's the reason why we lose more than 1 million people every year on this planet. When a Google self-driving car makes a mistake, it learns from it. And so do all the other cars, including all the unborn cars. All the future unborn cars will not make that same mistake again. And that means the capacity to learn and improve in robotic cars way outpaces the capacity to learn and improve in human brains. It's not just true for cars, it's true for all of AI. It's true for medical doctors, lawyers, accountants. Lots of people do repetitive work and leave open what the consequences are. But as a result, we're able to 10x the performance of the car every 18 months roughly at a speed that's unprecedented. So whatever you critique today about difficult decision making and things might go wrong, wait a year and it's going to be gone. These cars will just at some point just have 0 accidents. Thank you for coming. Plug in here?
Yeah.
Do you have an HDMI or?
Do. All right, well, thank you very much, Sebastian. Let's give Sebastian another hand. I think that was really fantastic. And it's incredible how things have transformed over the years, and the contribution you've made is really remarkable. My name is Danny Shapiro. I'm with Nvidia, and we're working with a lot of different companies. And what I want to do is take a few minutes, maybe dig down a little bit behind what the kinds of things Sebastian was just talking about, and tell you a little bit about what we're doing in this space and how the opportunity to maybe work with some of you in the future will be in the cards. Nvidia, as some of you may know, started as a gaming company. We're over 20 years old, but I would argue that we're one of the originators of the self-driving car. This was one of the very first things we did as a company here. So gaming is kind of at the heart of where our technology comes from. But it's really remarkable now how the GPU, the graphics processor, has evolved, and now it's gone from graphics into something called GPU computing, which is really transforming all types of computation. But more specifically, what we've been involved in is how do we simulate reality? Right? How do we create these virtual worlds? How do we do some really amazing stuff that's never been done before? And now, even most recently with artificial intelligence, it's not just simulating reality, but it's really trying to interpret or understand the world around us and using computers to do what we as humans naturally do. So gaming has grown up a little bit, and now this is sort of state of the art of driving games. And you look here now at the level of realism, the amount of computation that's going on here to be able to drive these screens, maybe very high resolution 4K screens at 60 frames a second. We're doing photorealistic rendering. We're basically doing physics simulation of how light travels and bounces and reflects. The physics of the vehicles is modeled, collision detection, and all kinds of other aspects. So gaming has really driven state of the art in terms of all different types of computation across industries. From gaming, we did a lot of work now in in professional graphics, if you will. This is a scene from The Life of Pi. You guys see that movie? Won Best Visual Effects a couple of years ago. So the water, computer generated. The boat, right, was a 3D model. And then we applied really sophisticated rendering techniques to create a photorealistic image. Again, it's mathematical computation to simulate how light would reflect and refract and to simulate the different kinds of materials. The tiger on the boat, it's a 3D model. And now we can also render fur. So again, somebody came up with an algorithm to simulate how fur would look and how fur would react. So companies like Disney and DreamWorks and ILM, all using the GPU, again, based on graphics technology. Now, all this transfers straight over into the auto industry. And so we've been working with automakers to enable them to make better cars, to use design techniques and use advanced simulation and engineering to create safer cars, and now even create more aerodynamic cars. So here's a computer simulation of work we did with Daimler, where they took a 3D model of the vehicle and actually run a virtual wind tunnel simulation. So again, very complex mathematical models here that can figure out what is the coefficient of drag of this vehicle. So this is actually something that they introduced at the Frankfurt Auto Show last year. And this car is a true transformer in that it elongates, the wheels change, the flaps and vents move, so there's an eco mode that it goes into to, again, have better fuel efficiency. We also have done a lot of work on other types of simulations. So here you see a crash test simulation. Again, massive amount of computation going into determine how will this car hold up in the event of a crash. And what's cool about this now is we have all this data that we've been able to model, and we can now peel back the layers. And you can see, well, how will the undercarriage hold up in the event of a crash? And it gives the engineer the ability now, instead of having to build a model and actually produce the vehicle and put it into this crash simulator or the crash test, we can simulate that and they can iterate on the design. So let's change the thickness of the steel. Maybe let's add some extra weld points and see how will that hold up. So the result of this kind of simulation, again, using mathematical models, very complex equations, we can really quickly iterate on the design of the vehicle and ultimately make much safer cars. Now, you may say, well, how accurate is this really? What we've done now is, over the years, we've been able to iterate on this, and you can see a video of an actual crash test compared to a crash simulation. And again, the results are so good now that they can very accurately predict how a real car will perform using standardized crash tests like this. Now, of course, our goal with self-driving cars is to not even have to use this. But the reason I bring this up here is, again, we're showing how the power of simulation can be used to really advance state-of-the-art engineering techniques. Now, Sebastian talked about AI, and that's really what I want to focus on. Artificial intelligence, and more specifically, deep learning, is essentially transforming every industry today. And kind of at a high level, what we're doing is using data science to write software. So instead of actually having to hard code algorithms, instead of having to program if, then, else kinds of statements and all these different scenarios, data is being used to create a neural network and essentially simulate how the human brain learns, retains information, and then acts on that information. So essentially, the process is training a neural network by giving it lots of information. And this is an offline process. This could take weeks, it could take months, but it's a lot of data collection. The data scientists work on this. But once we've built a neural net, then we can actually in real time go back, and as we feed data through the neural net, we can infer what the answer is, regardless of what the problem is. So in this case, if we've trained a neural net how to recognize all different kinds of images, then when we feed in the image, like this little girl, the neural net can extract information from that and tell us what it is, a girl eating a piece of cake. These neural nets already are all around you. If you use Siri, it's deep learning in action. When you do internet search, when you use Netflix and it recommends something. So these repetitive data types then are being used to train these neural nets that can then make advice, make recommendations, can help doctors diagnose cancerous cells, and detect pedestrians as you're driving in a self-driving car. We're seeing more and more consumer applications of these. There's a lot of really cool apps out in the market now Even something like a Pinterest now, you can take a picture of something using deep learning and artificial intelligence and actually go in and detect objects in the scene and do visual search to help you essentially shop for things that are in that image and make recommendations for those different objects. So we're going to see everything from finance to healthcare to automotive really leveraging deep learning. This whole area is exploding. If you guys aren't tracking it, I encourage you to just sort of do a few searches and look at what's going on in this space. But you have a lot of research going on at all the major universities. They're developing all kinds of applications on a wide variety of different frameworks. You have Amazon and Facebook and Baidu and Microsoft, everyone basically developing systems in the cloud to run AI applications. And then a whole number of startups, billions of dollars in funding recently for startups in AI, and established companies also leveraging this technology. So you see a number of automakers there, but it's virtually every company out there is looking at how can they leverage AI. Salesforce.com just announced their Dreamforce conference, and it's going to be all about artificial intelligence. So you have a database company, right? They're saying, how do we leverage AI to do their jobs better? I think the thing that's really key here, though, is there's been a couple of things that are sort of known as the Big Bang for artificial intelligence, and it's development in algorithms. It's the access to big data, right? You have everyone loading their images to Facebook or Google. So there's all this data that can be accessed. And then the GPU, the graphics processor, with its thousands of cores, basically became the processor of choice to be able to handle these very complex algorithms. Now in the automotive space, there's a huge amount of action going on here. A lot of startups, a lot of acquisitions, whether it's Google, whether it's Uber, Volvo, GM. This is a crazy space. So you guys are seated in the right seats, right? This is the place that you're going to be able to learn about this industry and be able to really make an impact. We're still at the start. There's a lot of action, there's a lot of people involved here, there's a lot of companies, but it's in its infancy. And the reality is that creating a self-driving car is very hard, very, very difficult. There's an infinite number of things to learn. There's all these crazy situations. You saw some of the videos from Sebastian. How do you teach a car how to handle all these situations? And there is no way you can write code to do this. You cannot do if this happens, then do that. Else, if this other thing happens, there's just too many crazy things. And so what we're doing is we're seeing the industry turn to artificial intelligence to be able to enable the car to make decisions, to enable the car to handle any possible situations. And I think, I can't speak to what's going to go on in the course, but I'm sort of maybe preview a couple things that I think might end up in the course, is that you're going to learn about neural networks and how to train a neural network and what a neural network does. But it's basically very sophisticated algorithms and ways that information there's inputs and outputs and many layers of inputs and outputs to come to a decision. And so I'll just give you one example, is if you have a camera that has a feed coming into the car, you have 30 frames a second, 30 images per second coming into that vehicle. And so that means you have 1/30th of a second to figure out what's in that image. Now, we as humans, we look at things and we recognize them instantly because we've been around the planet for decades and we've learned from little kids up to where we are now what all these different things are and how things behave and what happens, cause and effect. To the computer, though, this is just a bunch of pixels. Right? Each dot is a numerical value. And there's really no information in this image. And so what the computer has to do is figure out what is in that image. And so there's a variety of different techniques, but initially what we might do as this first layer is run an algorithm on surrounding pixels and try to figure out what patterns are in that image. And so the first thing is we're looking for edges. So sort of at each pixel, we start looking around for edges. Now, edges are really significant because edges sort of define objects. If you look around the room, you see edges. Well, there's edges around this screen. There's edges where the ceiling meets the wall, these pillars. And so your brain sort of eliminates some of the information in the middle, but it's the edges that help you define what those objects are and recognize them. So once we identify some of the edges, we'll group chunks of edges together to form elements. Might be a window, might be a mirror, might be a wheel. And then we group those elements together to form the objects. And so there's all these different layers at the pixel level that basically then output that this is a car. And it knows this is a car because we've trained it in advance. We fed it millions of images of cars and millions of images of trucks and millions of images of pedestrians, and eventually builds its vocabulary of what all these objects are. So again, this is a process that takes place. It's kind of two phases. The first is training, and once we've trained the neural net, then we can actually run it in real time in the vehicle to identify what the objects are. Now again, Sebastian talked about the process they went through, and there's a variety of different ways that you can develop a self-driving car. And so this is just one technique, but basically what we have is we start with a vehicle that has all kinds of sensors on it, cameras, could be radar, could be LiDAR, ultrasonics, and that sensor data is then collected, and then we do a number of different things with that data. Perception is one thing. We have to figure out what do we see and understand the environment. We also talked about earlier localization, being able to know precisely where you are on the map. And to do that, though, we need to have that data coming in. We need to get a map from someplace, whether it would be Google having a map, whether it's here, the consortium now that was bought by Daimler and BMW and Audi, or TomTom, or in Asia, the Zenrin. So mapping is a big, big part of this equation, and mapping companies, we've seen their market valuations go up incredibly. But then once we know where we are, and then once we can sense all the other cars and other objects around us, then that's where we need to figure out how to plan a path forward. And we continually are doing this, essentially 30 times a second, adjusting to anything that happens. So what I want to show is kind of a quick video of something that we demonstrated at CES, at the Consumer Electronics Show. Again, just some algorithmic work that we did very early on. After we trained the neural network, and we first trained it by giving it some signs, but then we can basically, like vocabulary, train it to recognize anything in the scene. So we taught it what do streetlights look like? What do digital signs look like? What do all different types of signs, in this case brake lights? So we're able to, first of all, identify what those objects are, train it, and then we can use that information to really build a complete environment model of everything that's going on around the car and be able to plot a smooth and safe path forward. But we're also able to, again, train things down to a very detailed level. And here we can recognize the difference between types of vehicles, whether it's an ambulance or a police car or a truck or an SUV. And again, that's very important because as a driver, this is when I was driving, we got pulled over. So the key thing is the car has to be able to understand the context that it's in, not just the shape, but precisely, is that a FedEx truck or is that an ambulance, right? Is that a police car? Do I need to pull over? Is it a motorcycle that's speeding, or is it a bicyclist? So again, all of these vehicles have different behaviors. And so that's something that we have to build in to this neural net. It's not only detecting the objects, but detecting the behavior, the expected behavior, and then also understanding what we need to do to avoid any potential accident. As you can imagine, this is a massive amount of processing. This is basically requires a supercomputer. If you think about it, most of the cars that Sebastian was showing had a couple PCs in the trunk, usually had some of our graphics processors in there doing the image processing, doing the neural network. So what we've done is we've actually developed a supercomputer for the car. And actually, I brought one here. We'll pass it around, but this is the Drive PX. And so this is, again, the size of a license plate. It has the power of 150 MacBook Pros. So this was designed basically using a combination of some mobile processors from gaming devices. We make them automotive grade so they can stand up to all the temperatures and conditions in a car. But this is designed to run deep neural networks. Okay, you can pass that around. And essentially, what we're doing is taking all the inputs, takes 12 camera inputs, radar, LiDAR, ultrasonic sensors. All that information comes in, and we're building a full 360-degree model of everything that's going around the car. And you saw some of those in Sebastian's demos. What's interesting, it kind of looks like a little bit like a video game, right? We're kind of recreating this virtual world and figuring out how to navigate through that virtual world. So since we brought this out a little over a year ago, we now have over 80 companies that are using the technology. A lot of them, I can't show the logos here, they're still in development, but we have major car companies, we have tier 1 suppliers, a lot of startup companies, and some other sensor partners. But essentially, this is kind of the platform that's being used to develop autonomous driving technology for cars, for trucks, and other kinds of vehicles. Even we have a version of it that is available for drones. So what I want to do is show you a couple of examples of some of our partners and work they're doing. And again, this is, again, sort of in parallel timelines of some of the work Sebastian was doing. But at Daimler, being able to run multi-segmentation networks to be able to classify cars and trucks and pedestrians. But one thing that I think that's really critical is not just deciding where is something in the scene that you want to avoid, but you need to understand where can you drive. And so there's something called free space calculation. And what we'll do is be able to, at the pixel level in the scene, be able to identify what's a person, what's a car, what's the street, what's a sidewalk, what's a sign. And this gives us this notion, this whole purple space now is an area of the road that we know it's safe to drive without anything being in our way. These neural nets, though, are really important in terms of being able to test how good the vocabulary of the car is, or how good it is identifying what's in the scene. This next clip is from Audi, and what we did was we actually trained the neural network in good weather, but we wanted to test it and went out in Germany in a snowstorm. And here you can see how accurate the system is at being able to identify cars out in the distance. Even when a human can't necessarily identify, we're able to sense and track different objects. Now, a huge benefit, of course, of these systems, too, is we're tracking 360 degrees around the car. These systems don't get tired, right? They don't text, they're not playing with the radio. So we have really 360-degree awareness. And again, to Sebastian's point, implementing these kinds of solutions are going to make a dramatic difference in terms of the number of accidents, injuries, and fatalities we have on streets around the world. One final example I want to show you in terms of how powerful these systems are is we were working with Audi on another project. And essentially, they had been working for 2 years with a smart camera system and traditional computer vision algorithms to detect street signs. So there's this German benchmark of thousands of street signs, and they, again, were trying to basically pass that test. So after 2 years of development, we kind of came along and we offered them up our deep learning solution. And they spent 4 hours training the neural nets. They weren't programming. They basically spent 4 hours feeding it massive amounts of images that had been tagged: stop signs, yield signs, speed limit signs, basically the entire database of German street signs. So after 4 hours of training, they achieved a better level of perception than 2 years of development by engineers in a traditional fashion. And so this, again, was a huge milestone. This was an opportunity then for them to realize that, okay, you know, we have to have cars in Japan or in China. I'm not going to hard code algorithms to recognize all the signs in those countries, but instead I can take that vocabulary, that database of signs for those countries, feed it into the system, and now my car can recognize all the signs in Japan or all the signs in China. And so this power of deep learning is really taking off. The ability to, again, train networks to recognize and to handle different kinds of situations is really significant. So one of the things that I wanted to show you is how we put all this together in a car. This was a test vehicle that we have, and we put cameras on it, we put LiDAR in it, and again, similar to the kinds of demos that we saw earlier, we're basically mapping this information in real time. This is the LiDAR scans coming back into the vehicle, and we can use this to build a map, and we can use this to localize and understand where we are. Then we also want to fuse these different sensor types together. Cameras are good at some things, radar are good at other things. LiDAR have advantages, but it's really expensive. By combining this, then we can understand the environment, we can create an occupancy grid and know where on the road we are and where on the road other vehicles are. We also use different kinds of algorithms, and I'm guessing you'll learn about some of this in the course, to do structure from motion, extract 3D information from 2D images. We're also running algorithms to understand what those different vehicles are. So using our cameras here, our front-facing camera and our rear camera, we can identify, is it a car? Is it a truck? Is it a motorcycle? And then we put all this stuff together. We kind of, again, build this 3D model. We know how fast we're going. We can figure out how fast the other vehicles are going. Are we accelerating too fast? Do we need to brake? Then we bring in the road map. And so then we can also know precisely where we are. We need to know from the lane markings, but if there aren't lane markings, what do we do? We need to know, is a lane a turn lane? Is it an exit lane? Is it a merge lane? And so a lot of that data comes externally, and we merge that in together to decide how we're going to drive. And then finally, we need to pull it all together, and we add a behavioral model to understand, again, what the other cars are doing, to anticipate them, and make sure our car is driving like a human and not like a computer. I think that's critical in terms of the computer could drive very precisely, better than any of us, more accurate. It's doing incredible calculation and computation. But no one's going to enjoy that if the car accelerates too fast or brakes too fast or turns too fast. Both the occupants of the vehicle and those around the car will not enjoy it. So the key here is to be able to build behavioral models into the neural net as well to enable it to drive much smoother. So the last example I want to give basically takes us one step further. And instead of training our network to recognize specific objects, what we wanted to do here was a whole end-to-end solution where we trained the network based on taking in the scene and mapping that to the steering wheel. So we're not explicitly trying to identify a car or a lane or a pedestrian, but in the context of the world, what does that scene look like and how do we drive the car? And so the benefit of this is it's not dependent on any one item. It requires a lot of training. We just did a test. We wanted to do a simple proof of concept, and so we did 3,000 miles. We'd never advocate that for a production vehicle, but for this test, we actually had really great results. So the first time we took the car out, though it hadn't been trained, we took it out in a parking lot and we set up some cones. It was like the teenager. It ran over the cones, right? It couldn't stay in the lane. It hit some garbage cans on the side of the road. But the fact then we started teaching it by actually driving and had a professional driver, it learned after 3,000 miles. So this next clip basically shows after 1 month and 3,000 miles, we were able to have the car drive itself. And it could do this like through a construction area with a bunch of cones. It could do it on country roads. It enabled the person to not have to pay attention. This was done in New Jersey where there are no laws about self-driving cars. It's the Garden State Parkway. But what's critical here is you see there's no lane markings. And so the car continues. It doesn't freak out that there's no lanes because it wasn't taught to have lanes. When there's lanes, it uses it. If there's no lanes, it doesn't use it. Here, there's a dirt road, right? It's still able to navigate. And even though it's not a normal scenario, it does what you or I would do. You would just keep driving. So I think, again, the key thing here is with just a little bit of training, it was able to accomplish a lot. We need to do a lot more training. Now, in addition to Udacity, I just wanted to do, this is the one shameless plug, we put on something called the GPU Technology Conference every spring. So there's one coming up in May in San Jose. But it's been so successful, we're taking it out on the road. So if you guys are interested in learning more about AI for any field, but in addition for self-driving cars, there's these venues throughout the world and a lot of additional content online. So where is this going? I don't know how many of you have heard of RoboRace. This is something I think a lot of you guys are going to be interested in. This is a model of a Formula One class vehicle that's going into production, limited production. But as part of the Formula E, the electric Formula racing season for 2017, there'll be 20 of these vehicles on the track, 150 plus mile an hour. What you're noticing here is there's no cockpit, right? This car is an electric vehicle, but it's going to drive itself. It's outfitted with a bunch of sensors, cameras, LiDAR, radar, and it has the Drive PX2 inside. So essentially there's going to be 10 teams, 2 cars per team, so there's going to be 20 of these cars out on the road. They're all identical, except for the paint and the software that's going to get loaded. So the robo race organizers are basically going to have sponsored teams, but they're also going to have some crowdsourced teams. So I have a feeling that the people who graduate from the nano degree are going to have the chops to basically submit their software and basically earn a seat on the track at the robo race circuit that's going to start this fall in Hong Kong and basically have locations all over the world. So this is going to be a really exciting competition. Again, every car is the same. It's now becoming a data science and a computer science challenge more than a traditional driving kind of motorsport. So stay tuned on that. The last thing I wanted to talk about was simulation. And this kind of gets back to the video game side. And one of the things we've been doing is, again, using computer simulation. In fact, this is a gaming engine that we developed a bunch of algorithms for auto valet and self-parking. And so we wanted to use simulation to develop the system and use it to train the neural network, but then also to be able to use simulation to test the effectiveness of our algorithms. And so one of the key things I think people are asking right now is, how do we know these cars are safe enough to put on the road? And the federal government and state governments don't really have an answer for this. And so the industry is working closely with these federal agencies. But I think what we're going to see is a lot more simulation being used to test the effectiveness of the algorithms. And also what we can do is we can simulate very hazardous situations. Here's a parking lot that we've simulated. This is actually an Nvidia parking garage that we modeled in 3D and developed a way that we could test and figure out if the car is smart enough to park itself. But I think the reality is not just parking, but there's going to be a lot of scenarios where there are kids playing in the street, whether they're very dangerous intersections, where you can't test with humans. It's too dangerous. And so what we're going to see is a lot of simulation being used to prove the effectiveness of the algorithms. And I think you guys will probably see a lot of that too in the course that you take. And so if we do our job right, we are going to eliminate the need for this kind of simulation. Thank you very much.
We'll do a quick Q&A. So we're gonna do a quick Q&A. If you have any questions for Danny, unfortunately, Sebastian had to go. So, all right, we have first question in front.
Nice talk.
Perfect.
Can you explain your board a little bit, like what kind of input you need to have, and what kind of output, and what kind of simulation you do, and what kind of calculation can you do, like besides autonomous driving?
Well, I think that was about 5 questions, but I'll do my best to remember what they all are. So inputs and outputs. Again, this is a reference platform, and a lot of car companies are using it or they customize it. But essentially, sensor input comes in, so it's cameras, radar, LiDAR, ultrasonic sensors. We get map data. We could get vehicle-to-vehicle data, vehicle-to-infrastructure data. Think of it, it's a computer platform. It's an open system for automakers to develop their own code. They get a lot of algorithms from us, a lot of software libraries and tools, but the application is being built by our customers or people who will take the class. So the algorithm development is varied, right? No car company is really doing the exact same thing, but the concepts of what they're doing, the ability to train the neural network how to recognize objects or how to take different types of inputs and fuse them together is kind of the core of autonomous driving. AI can be used for basically anything. The Drive PX that I passed around, that's our product for the vehicle, but we make products that go into robots, that go into your PCs, that go into the cloud. And so the key, though, is a lot of the code that's developed can run in the cloud, but also run in the car.
Aditya, you have a question. Great. So there's a whole cadre of Tesla Autopilot folks here, and Aditya is part of that team.
Hey, thanks so much for the talk. I was curious to hear your thoughts on where the industry is going in terms of vehicle-to-vehicle infrastructure and communication. I know Sebastian and you hinted at it earlier in terms of being able to sort of learn at a fleet level, but I think it's interesting just in terms of applications like doing sensor fusion at the level of like multiple cars, doing sort of the optimal like vehicle distribution to minimize traffic over routes, and all sorts of other things. So just curious to hear your comments on that. Thanks.
Need another mic.
I think we just have one.
Good. Thanks, that's a great question. You know, the more information you have, the better it is. And the more layers, the more different kinds of information, the more reliable the system will be, or the more capable the system will be. I think V2V is a long ways off. And it's going to be, you know, one of those fax machine problems where there's going to be a few cars out there, but they're not going to have anybody to talk to initially. If we see some form of regulation put in place that requires, that mandates V2V, you know, I think that will certainly help on that front. What we've been doing all along is we can't wait for it, we can't rely on it. So everything we're doing is basically creating an autonomous car that truly is autonomous, that will drive on its own and it doesn't need that external input. That's not to say the car's not connected. I mean, we want to get information from the cloud. It's just not going to be real-time information, right? We'll get the map data, we'll get updates. We'll send information to the cloud, and that will be used to train the neural network, and then eventually we'll get a software update. I think the key thing here is that we're not talking about our car learning in real time, and if I drive it really poorly, it's going to learn how to be a bad driver. But the software is going to come from the manufacturer, and that software will be basically trained with professional drivers. And data might be crowdsourced and anonymized, but it'll be tested and certified and have to hit a minimum bar, you know, that the federal or state government mandates, and then it'll end up in your car. Once V2V is there, it'll be great, right? We'll know that a car is going to turn in front of us rather than trying to have to guess and figure it out. But you know, and for traffic flow, same thing, right? We can, if all the cars are talking to infrastructure, they can be rerouted in different ways. AI is going to play a huge, huge part in traffic congestion mitigation, and I think it will be able to do this even with cameras. Right? We can put cameras around a city, and they can monitor the traffic flow and be synced up with the timings of the lights, and the system can learn how to improve the timing to reduce congestion. I mean, when you drive down El Camino or whatever, I mean, sometimes you're going, oh my God, I can't believe how screwed up these lights are. All that can be solved really easily with AI.
All right, so it's Friday night, it's late. We'll take one more question and then we'll wrap it up here.
Thank you for a very enlightening and inspirational talk tonight. My question is, I see a lot about dealing with objects and understanding objects, but what happens when a car comes into a tornado or into a flood or into a hurricane or some high weather condition or high wind condition? How will it deal with that?
So weather is a really important one, and I'll maybe start with the easier answer, which is you have more predictable weather, like rain, fog, snowstorms, things like that. And what we've seen is we can actually have better levels of human perception with our sensors, with a variety of sensors, and even being able to do image processing, right? We can, some of our classic things, we can remove raindrops, right? So the camera's taking a really bad rainstorm image in, but we can sort of apply image processing techniques and clean up the image so that the brain of the car is operating as if it wasn't raining. You know, I don't know if we could ever be able to handle situations that humans really can't handle, right? If a flood comes in and washes your car away, there's really nothing you can do about that, right? I mean, there's sometimes a plane comes in and lands on a freeway and hits a car. I don't think there's anything we can do about that. So autonomous cars are going to dramatically reduce the number of accidents and injuries and fatalities. Nothing's perfect in this world. I don't think we can set a goal of 0, but the reality is I don't think we're going to get to 0.
All right, thank you very much. Let's give Danny another hand. All right, just in conclusion, I just want to thank everyone again for coming. We had some wonderful corporate supporters this time, including McLaren and Greylock Venture Partners. The folks in this crowd are from just a huge variety of self-driving car startups and established companies, including McLaren, Tesla, Mercedes-Benz, Baidu, Nvidia. There's a few stealth startups in here. Valeo, our friends from DeepScale that are doing software for some of the large manufacturers, and Uber. So stick around, meet people, talk, and have a good time. Oh, and our next few events are going to be on healthcare, so look out for it. Thanks.